It's always a good idea when you're going over your tests to make sure you make your corrections, because the tests are where you're gonna study for the final. So if you go through and you get each test perfect in the corrections, and obviously it's not going to change the grade, but it will help when you go to study for your final, because then you only have to study the tests. Because what I do is I take the questions from each of the tests and I kind of adjust them a little bit, change the values, but the types of questions are going to be the same. So that way you have something to really go back to and study off of for the final. So definitely let me know or come and see me. I am on Zoom right before this class and then right after this class. So we can meet and meet one-on-one and see what needs to happen to make sure that your grades are coming up. Okay, so with that said, what we're going to do today is we're going to jump into chapter 10. So chapter 10 is what I call my derivative toolbox. So there's 6 sections in chapter 10, and the first 4 of them are just giving you tools to be able to find derivatives of anything. So right now, our only tool is our power rule. That's the only way. Well, we have 2 tools. We have the definition of the derivative, and then we have the power rule. So those are the only 2 things that we have at this point to be able to find derivatives. But what we're going to find is we're going to get into functions that have other things in them besides just a polynomial. So we have to have better tools and more tools. So the way I describe it is, my husband's an electrician, and when you're building something or when you're putting things together, there's certain tools that you use that work better in a situation. So for instance, he has to put, the plates and the switches and plugs and all of that. Well, the best tool is not a hammer. That is a terrible tool to use when you're trying to screw something into the wall. You want to use a screwdriver. So you want to be able to know which tool to use when. And so that's the mindset that I want you guys to have, is that there's certain tools that you need for certain types of functions. So let me share my screen, and in your this is in your module for module 2. So now we're in module 2, and these are all the tools that you're going to have, that we're going to use by the end of chapter 10. And so this is really the only thing you're going to need for chapter 10 test, for the second test, is all of these tools. But you have to know how to read them. Okay, there's very specific math language here, and so you have to know how to read them. So for instance, this is our power rule. We already know what the power rule says. The power rule says if you're given a function where it's x raised to the n power, you're going to drop that n to the front and multiply, and then you're going to subtract 1. So being able to read the power rule is going to be really important, and remember how to do it. Then this next section is these are called 4 special derivatives. Now, if we were in a STEM calculus class, we would go through each one of those, and we would use the definition of the derivative, and we would come up with these derivatives. In this class, I'm not going to walk you through that. All I'm going to do is say, hey, these are the rules. This is how you find the derivative, and this is what the derivative is. And we'll go through each one of these today. Okay, so these are your 4 special derivatives. And then probably today we're going to start on the product rule, and then Thursday we'll finish with the quotient rule, and then we'll practice with those. And so you can kind of see the product rule is being able to read this. So what that means is the product is the answer to a multiplication. So if you notice right here, right here, we are multiplying two functions. Okay, so we'll talk about, well, what do we do when we multiply two functions? And then the quotient rule is you're dividing two functions. So what do we do when we divide two functions? Okay, and then we'll get into the chain rule and then the generalized power rule, which kind of goes with those four special derivatives. Okay, so these are all the special tools that we're going to be able to use by the end of chapter 10. Your job is to know when to use which one. That's your job, is to be able to recognize, oh, this is I'm multiplying two things, so I have to use a product rule, or, oh, this is a exponential function, so I have to use the exponential function derivative. Okay, so this, I wanted to give you this so that you have it. It is in your module under the formula sheet, and so you already have it. So I would print this up and have it next to you when you're doing your MyMathLab. Just kind of have it there, know how to read it, understand what it's saying, you know, how to read that math language and get comfortable with it. Okay. All right. So what we're going to start with is 10.2. So we're not doing 10.1. We're just going to do 10.2. So 10.2 is all about these four special derivatives. Okay. So remember with get a graph over here. Okay. So with the derivative, right? Derivatives are all just about the actually I don't want this one. The derivatives are always about slope, right? That's all a derivative is just finding the slope. So with this first one, this e raised to the x, e is a natural number, all right? E you will see in nature, and e is 2 point, I believe it's 128. Let me get it real quick here. I gotta find it. Yeah, 2.718281828, and it keeps on going, but it doesn't repeat itself. So just like pi is 3.141 blah blah blah, e is also a number. So when you see the letter e, don't think of it as a variable. It's actually a number, and it's used in nature. So that's why it's called the natural number. So in anytime there's growth or decay, that's when you would see the natural number, especially in nature, is, you know, how things grow, how things duplicate, how things, you know, population growth, radiation decay, investments. If you remember in 1324, when you did the finance chapter 3, you used E a lot when you were doing the continuous compound interest, right? Your money is growing. So that's what E represents. So if you're graphing E, it looks something like this, right? It's an exponential growth, and it looks like that. Well, if I were to put, see if I can do this. If I were to put a tangent line right on this function, and I were to move this tangent line, and I were to move it and follow my function, my e function, what you would see is that my slope actually follows my graph. So it's actually the exact same shape as my graph. So your first tool is when you have the derivative, so that's what this is saying. It's saying find the derivative of e to the x in terms of x. That's what this d dx is. Remember, it's an action, right? It's saying, when you see this, it's saying find the derivative. It's just a set of instructions. Mathematically, we don't do anything different. It's just finding the derivative. But the d dx is saying actually take that action, find the derivative of e to the x. And so the derivative of e to the x is e to the x, because if I'm finding the slope anywhere on this function, you can see it just follows the function. It ends up being the exact same shape as the function. Okay, so again, remember your job is to find or to know which tool to use when. So when you see e raised to the x power, that's when you know you're going to use this particular derivative. So the derivative of e to the x is e to the x, period. That's it. No thought process. You don't have to give me an explanation why. I'm just giving you the tool and I'm telling you this is the tool you're going to use when you see e to the x, or this is the derivative you're going to use. Okay? Any questions? Okay, so this is my e to the x function. This one, the derivative of b raised to the x. So b is a base. So that's a number, any number. All right. So again, if I were to get a graph and I wanted to, let me change colors here. I wanted to graph maybe the function 2 raised to the x power. So one thing I want you to notice is now all of a sudden the variable is in the exponent position, right? Up until this point, all of our variables have been the base. So the base x raised to 2, or the base x raised to 3, or the base y raised to 4, whatever it is. Our exponent was actually the number. Now with this derivative, now our exponent is the unknown. It's our variable. So our base is a number and our variable is the x. That's how you know, okay, this is going to be my what's called an exponential function. This is called an exponential function. Okay, so remember the first week of class, we talked about doubling, when things double. And so I said, you know, if I gave you $1 on day 1, and I doubled it every day, how much would we have at the end of 30 days? And it was like $1.5 million. So that's what the exponential function does. Because if I said 2 to the 0, that's 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. You can see every single one of these are doubling. Okay, so that's what the exponential function does, is it doubles every single time I add a number to my exponent. So it just keeps doubling. And so once again, as we're doing this, it starts out slow and then it gradually increases. So you can see it is, oh, I didn't want to do that. I don't know why I did that. I don't like that. I don't know how to get rid of it now. Nah. Okay. It is not pointy. It's a curve. Okay. So this is my 2 to the x function. And you can see it's basically the same shape as e to the x. The only difference is my base can change. So if I had the function 3 to the x power, what happens is now that 3 to the x, it's going to start growing even faster because now I'm tripling. So I have 3 to the 0 is 1, 3, scroll down here. 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. Do you see how everything is tripling? 3 to the fourth is 81. So it's really starting to grow. So it's actually growing faster. So the bigger my base, the faster it's going to grow. Okay. So the function is going to be a little bit different. The derivative is going to be a little bit different depending on what my base is. Okay. So the tool, the derivative of b raised to the x power is b raised to the x power times ln of b. Okay. So let me show you what I mean by that. If I have the function 2 to the x and I asked you to find the derivative of it, you are literally taking whatever my base is, and I'm repeating it, times ln of whatever my base is. And this is my derivative. Okay, so all you're doing is you're looking to see, okay, which tool do I need? And then plug it in. Just plug in what it says. If my base is 2, I'm going to plug a 2 in here and here. If my base is 3, I'm going to plug in a 3 here and here. So if I have, find the derivative of 3 raised to the x power, it's 3 raised to the x power times ln of 3. Okay, now ln is the natural log. Okay, so the natural log is the inverse of e, because the natural log is the log base e of whatever my function is. So these are inverse operations. Okay, so that's what the ln is coming in as. So it's just whatever your base is raised to the x power times ln of whatever your base is. Okay, so all you're doing is you're just plugging things in. And for whatever reason, I think because this is so, you don't have like a full understanding of why it is what it is. Sometimes these 4 are the ones that catch people the most, because you're literally just plugging it in and people go, this can't be this easy. And it really is this easy. You're just plugging in. You're identifying which rule to use, and then you're using that rule to get your derivative. Okay. Any questions on that one? Okay, the next one is when you're finding the derivative of ln of x. So ln, again, is the inverse of e. So I'm going to go back up to my e function and show you what it looks like. So if I have, this is going to continue on here. My ln function is going to look something like this. So it's literally the inverse. This is my e function. This is my ln of x function. So it is going to look a little bit different, right? It's not going to be the same thing because it's the inverse of e. It's the opposite of e. So with this one, the derivative of ln of x is 1 over x. Whatever this is, 1 over whatever that is. And that's your derivative. That's it. This can also be written as x to the negative 1. Just keep that in mind, right? So ln of x, the derivative is 1 over x, but another way to write that is x to the negative 1. So this is going to come back to us. This x to the negative 1 definitely comes back to us later. Okay. And then the last one is a log. So remember, a log is just the opposite. These are opposites, and these are opposites. These are called inverse operations. This e to the x to ln and b raised to the x and log base b of x. These are inverse operations. So the inverse of a log base b of x is 1 over x times 1 over ln of whatever that base is. The other way to write this is 1 over x ln of whatever the base is. So you can write it either way. This to me is a little bit easier. It's more compact. And all I did is I just multiplied. 1 times 1 is 1. X times ln b is x ln b. Okay. So again, whatever that base is going to go right here. Okay. Whatever this x is going to go right here. Okay. So let's try a couple. And then I'll show you a word problem that we can work through. Okay, so just like when we were doing polynomials, you're going to find the derivative with every single term. Just do it individually. Okay, so remember, we have the power rule. That's our one tool. And now we have these 4 different tools. So any one of them is fair game. And again, it's up to you to be able to recognize it. So I have ln of x. So I look up here and I go, okay, which one is it going to be? Well, here's my ln of x. The derivative of ln of x is 1 over x. And I'm done. Okay. Plus, I see I have e raised to the x power. So my derivative of e raised to the x power is e raised to the x power. And the 2 just comes along for the ride. So it's 2e raised to the x power. So I'm just repeating it. Okay? So look and see, ln, ln. E raised to the x, e raised to the x. And then I have minus x. So now I'm back to my power rule. So the derivative of negative x is -1. So remember, we have a 1 here. We drop it to the front and multiply. 1 times -1 is -1. When I subtract 1, I get x to the 0, which equals 1. So that's why the x goes away. And then the 4 is a constant. So the derivative of a constant is just 0. So this is my answer. I just took each piece and found the derivative of each one. Okay. Any questions so far? Okay, so for this one, notice it has ln of x to the 4th power. All right, so what you need to remember is ln of x is an exponent. Okay, if you remember ln, so if we had the function e raised to the 4th power equals, let me find it real quick. Is 54.598. And I asked you to write this in logarithmic form. It would be ln of 54.598 equals 4. So remember, it's just a rearrangement of an exponent. That's all a natural log is. Okay, so what I have here is I have this exponent 4 on an exponent. So do you remember your exponent rules? Let's do it over here. So remember your exponent rules. You have the product rule, which means if you have x cubed times x, say to the 4th, you get x to the 7th, right? You add. When you have the quotient rule, if I have x cubed divided by x to the 4th, I get x to the -1, right? Because we subtract. And then there's the power rule for exponents. The power rule says if I have x cubed raised to the 2nd power, I multiply these two. Okay, so since a log and an exponent are the same thing, the rule still applies. This is an exponent on an exponent. This is my power rule. So what I'm going to do is I'm going to rewrite this. So again, I'm going to rewrite this as 4 times ln of x, and then just keep writing. So I take this 4 and I drop it to the front because it's an exponent on an exponent. So now I can find my derivative. So ln of x is 1 over x. So this is 4 times 1 over x. And then the derivative of 5x is just 5. The derivative of -3 is 0. It goes to 0. So when I put this all together, I get 4 over x plus 5. And that is my derivative. Okay, so sometimes you have to peel your exponent off when you're looking at the ln. Just peel it off and put it to the front, and then you can go ahead and go, do the normal finding the derivative. Okay, any questions on that one? And you'll get lots of practice when you do your homework for tonight. You'll get lots and lots of practice on these. Okay, so who can tell me which of these 4, so 1, 2, 3, or 4, which of these four am I going to use for number 3? Either put it in chat or unmute yourself and let me know. What do you think?
Either 1 or 2.
Okay, so let's narrow that down even further. If I'm going to use 1, there has to be an E in it. So which one do you think it's going to be?
2.
There you go. There you go. So if it's raised to the x power and there's no E, then you're going to use 2. Okay, so the only time you're going to use 1, the e to the x, is when there's an E in it. Okay, so here we go. The 500 just comes along for the ride. And now my base is 0.6 raised to the x, so I'm going to repeat it. That's this part right here. And then times ln of 0.6. And I'm done. That's it. That's all I can do. Because there's an unknown, this x, I can't just multiply 500 times 0.6 because there's an x here. That means there's some number here and I don't know what it is yet. So if I don't know what it is, I can't do anything else to this. Okay. And again, the 500 has to come along for the ride. Just like the 2 on e to the x on number 1 came along for the ride, the 4 on number 2 on ln of x comes along for the ride. If there's a multiple or a multiplier, that just comes along for the ride. And then you do whatever it is for the derivative that you're using. Okay. All right, number 4, which one are we going to use? 1, 2, 3, or 4?
4.
Okay, number 4. And the reason is because we have log. So log, log. So the only difference is now my base is showing, right? I know what that b is. I know what the base is. So my derivative is going to be 1 over x times ln of whatever the base is. So the base is what's going to change. So if the base is 5, it's going to be ln 5. If the base is 1,000,000, it's going to be ln x ln x ln 1,000,000. So just whatever that base is, that just goes right there. Okay. And then the last one, we have a radical. So the first thing I'm going to do is rewrite it without that radical. So remember, the 3, the index goes underneath. So it's 1/3. Now I can do my derivative. Okay. So here we go. The derivative, oops, this is not the derivative. So the derivative, so 7 raised to the x power, I'm going to use my exponential function. So it's 7 raised to the x power times ln of 7 minus, and now I use the power rule. The 1/3 comes to the front, and then I subtract 1. So I get negative 2/3. That doesn't look good. Negative 2/3. There it is. Okay. And then if this was, your test, this is a great answer, right? Nothing wrong with this answer. But if you want to clean it up a little bit and take it back to the radical, it would look like this. So 1/3. So 1 is my numerator, 3 is my denominator. The negative exponent says this has to go in the denominator. The 3 is my index. The 2 is the exponent. So this would be your extra credit, the second one. Okay. Now, as we're learning all these tools, what you're going to find is there's not a lot of application until we get into the last two sections. Or actually the last section is when we do a lot of applications. But there's one application I can show you right now that actually works, and it is something that you can use, especially if you're going to buy a car. All right, so we have the estimated resale value. This is capital R in dollars of a company vehicle after T years. So again, always notice what your variables represent. The capital R represents the resale value. The T represents the number of years. Okay, so that's going to be key. So then you'll know where to put the information in. So this is a function that shows, so the 20,000 represents the starting amount. Okay, the 0.86 represents the percent. So you can look at it as 86% for every year that you own the car. That's what your car is worth. Okay, so if we're looking for the derivative of this, because we want to find the rate of depreciation, right? So when you see the term rate, and this is going to be key when we get into the word problems and related rates, rate equals derivative. So remember how we talked about instantaneous rate of change. We talked about slope of a tangent line. We talked about marginal. We talked about differentiation. All of those terms means derivative. When you're looking for a rate of change, that still means derivative. Okay, so again, you're having to put all these terms together so that when you see that term, you go, okay, I know what I'm doing. I know I'm finding the derivative. Okay, so we're looking for rate of depreciation. So depreciation means it goes down, right? That makes sense. When you buy a new car, the minute you drive it off the lot, you just lost $5,000 to $7,000 because it depreciates that much. It's no longer a new car. Okay, so the 20,000, that's a nice number. That is so unrealistic right now. There are very, very few, if any, cars or trucks that you can buy for $20,000 as a brand new vehicle. Okay, we're talking now $30,000 to $120,000 cars, and I'll show you an example of that. Okay, so here we go. So the first thing we're going to do is we're going to find the derivative. So finding the derivative in terms of t. So again, the 20,000 comes along for the ride. And if you notice that 0.86t is just like b raised to the x power. Okay, our unknown is the t. So the derivative of this is 0.86t times ln of 0.86. That's our derivative. Okay, we took this part right here. This is the derivative. And I cannot emphasize this enough. Put a big old star by this one, because you will see this on your test. This will be one of them that will be on your test and on the final. And I cannot tell you how many times students will do 20,000 times 0.86t and forget the ln of 0.86. So this part right here, you have to remember that part. Okay, that's all part of the derivative of 0.86 raised to the t power. Okay, so now we can use this. This is our derivative. Now we're going to find out, all right, how much does our vehicle depreciate after 1 year? So the depreciation after 1 year, so notice I'm taking the t out and I'm plugging in 1. So this is actually telling you what to do. I take the t out, I plug in 1, and then I calculate. So you have to have a calculator for this. Okay, there's no way you can do this without a calculator. So you're going to literally, because it's all multiplication, just plug it in straight through. So I'm going to go 20,000 times 0.86 raised to the first power, which is just 0.86, times ln of 0.86, and then close my parenthesis. So I get a negative 2,594.15. Okay, depreciation does indicate that I'm going to have a negative value. So again, make sure your answer makes sense, right? So when you see the term depreciation, you know you're going to get a negative slope. If it said rate of appreciation, that means how much is it increasing? So it would be a positive slope. So here's what this means. Let me type it out. So after 1 year, my car's value goes down by $2,594.15. That's what that means. That's what that whole depreciation, rate of depreciation means. Now, that doesn't look like very much, right? That looks like, that's not that big of a deal. So what happens then, and I can say this because my husband just bought a brand new truck. That's what he paid for it. Now, 2 months ago, we went and looked at the same truck and it was $80,000. He got it for 56. You're going, man, that's a great deal. That went down, $15,000. The reason is because 2 months ago, it was 2023. He just bought this truck 2 weeks ago in 2024. So just waiting those 2 months, it's brand new. It had 80 miles on it and it was a 2023 truck. They needed them off the lot. So there's very strategic ways to get a good deal on a car. A lot of times if you wait till the end of the month, that's a good, because they have, quotas at the end of the month that they want to sell a certain amount. Waiting to the end of the year and buying the previous year's truck or vehicle will save you a bunch of money. 56,000 is still a lot of money. It's killing me. Luckily, it's for his business, so it doesn't come out of the household income, but it's still a lot of money, especially since the last brand new truck he bought was in 2000. So the poor man has had the same truck for 23 years and he still has it. So he definitely, gets his worth for it. So let's try this. Let's see what's going to happen. So now if we have, so again, that 20,000, I'm going to put 56,000 times 8.86 raised to the first power times ln of 0.86. So now let's see. Obviously, that number is going to go up tremendously. And it is negative $7,263.63. So that's how much it depreciates after 1 year. Okay, that's a pretty high number, right? $7,000. If I told you you're going to lose $7,000 in 1 day, you probably would hesitate a little bit before you do anything. Okay, so now let's go back to this one. Now what happens after 2 years? And there's a point to this. This is a life lesson for you guys. There's a point to this. So now let's try it after 2 years. So we're going to find the rate of depreciation after 2 years. Okay, so you can actually kind of have an understanding of what all these numbers mean. So again, the 20,000 is the new, what you paid for it, or the new value. The 0.86 is what it's worth each year. So in other words, what you're losing is 14%, right? Because 14 plus 86 is 100%. So that's what the value, that's the value of the car. That's how much it goes down, is about 14%. All right, so here we go. Does anyone have a number for me? And again, it should be negative. And because math is a action, it's an action, make sure you are doing these on your calculator, because then you're practicing how to use your calculator. Some of you have the TI 30XS, like what I have. Some of you have an 84. Some of you have, a Casio. So make sure you know how to use your calculator. That's a decimal point right there. All right. So what does this mean? Each year, the car's value goes down by 2,230.97. Okay, so do you notice that the number is different now? Right? Now we're finding the rate of depreciation is actually reducing. So after 1 year, it reduces by 2,500. After 2 years, it reduces by 2,200 each year. So each year is important. Okay, so the rate of depreciation is actually going down. Okay. So now let's try it after 3 years. So the rate of depreciation after 3 years, so 0.86 raised to the third power times ln of 0.86. And again, your answer should be negative. And this is where you'll have to use your hat key.
Is it negative 1,918.63?
Uh-huh. So 1918.64, because the 6 makes the 3 go up 1.
Yeah.
Okay. So again, do you see how it even drops even more? Here, it dropped, 300 and, what is that? $364. Now it's dropping by, what is that? 2230.97 minus 1918.64 by 312. So it's dropping less every year that you have it. Okay, so the lesson on this is, do you know how long I'll put it this way, it's decreasing by 8.64 each year. So do you know how long most people hang on to their cars? Any idea? Before they trade them in?
I think like either 5 or 10 years.
Okay, that's actually very high compared to the average. Most people turn their cars in every 2 years. They get tired of it. They go, don't want to do any maintenance on it. Don't want to buy new tires. Don't want to have to get new brakes, whatever it is. So the majority of people will turn their car ins every 2 to 3 years. So what happens is your rate of depreciation is actually very high. If you wait, so let's try, if I say, if I'm like my husband, right, and I have a $20,000 car, and let's say I want to know what is my rate of depreciation after 10 years. Well, when you do that, your number goes way, way down. It goes down to a negative 667.55. So I am under $1,000 per year that it depreciates. So the rate of depreciation slows down the longer you have your car. Think of it this way: when you give up your car after 2 years, you're giving up a lot of value of your car, because you and I both know that when you go in and you trade in your car, they never give you a good trade-in value. It is very rare that somebody will offer you a good trade-in value. And so you're losing money. You're losing money by just trading in your car every 2 to 3 years. If you hang on to it, that rate of depreciation slows way, way down. And then you get the value of the car much much clearer than, or much easier than, if you trade it in every 2 years. The other thing is, and I can attest to this wholeheartedly, not, I didn't do it, but someone very close to me did, a couple different people, leasing the cars. So when you lease a car, it sounds really good. Like, oh, my car payments are only $200 or $300 a month. So your car, when you lease a car, your payments will always be less than if you bought the car. But where they get you is on the back end of it. So you may have a 2-year lease. When you go in and you trade in your car after 2 years, because they give you a choice. You can either pay the car off, as if you're buying it, or you can trade it in and get another car to lease, right? So when you trade it in, they go through your car with a fine-tooth comb. And if there is one thing wrong, even a little tiny stain on a seat, they upcharge you. And so they really nail you on the back end of those leases. And that's where they get their money. And it's happened over and over and over again. And so what happened to my close family member, they went in and they went to trade in their lease to buy a car. And so the amount of money that they owed on the lease, they added it onto the loan of the car that she was buying. And so now her car, she owes more on her car than her car is worth. And so she is upside down in that loan. And so it's going to be a long time for her to get out of that loan, unless she really pays heavy on it. So don't ever lease a car unless you are in dire straits and you have no other choice. Sometimes businesses will lease several cars, and that's just a write-off. But as a personal car, I would never recommend leasing a car. It's just they hide those fees, and there's nothing you can do. You cannot get out of those fees. Okay. All right. Any questions on this type of problem? And remember, your extra credit is going to come from, can you interpret your answer? Okay, that's where the extra credit's going to come from on this next test, is can you interpret these answers and the answers that you get. Okay. All right, so that's it on that one. Now what I want to do is we're going to jump to the next tool. So let me show it to you. So the next tool is our product rule. Okay, so our product rule we use when we are multiplying two things together. Okay, now sometimes you can get out of these. Sometimes there's a way to do these problems where you don't have to use the product and you don't have to use the quotient rule. All right, if you can get out of it and you can see it, then 100% do that. But if you can't, then we're going to do something called the product rule. So how do we know it's a product? Well, on this first example, you can see it's x to the fourth times x squared plus 5. Okay, so I have two different things that I am multiplying together. So I'm going to use a lot of color here today to help identify these. So this one, I'm going to call my first function. And this I'm going to call my second function. Do you see how I'm multiplying those two? And do you see how it lines up with this? The first times the second. Okay, so again, this is where you have to know how to read these. So if you have a function where you have the first times the second, then the derivative of that, so now you're reading this, the derivative of the first times the second function plus the first function times the derivative of the second function. All right, now it looks big and complicated and terrible. All right, but I'm going to give you a really easy way to do this. The easy way to do this is you are going to come up with a forecast of characters. If you do it this way, you will never, ever, ever, ever get these wrong. Because all you're going to do is set up your forecasted characters and plug them into this function. So what are the forecasted characters? Well, we already know we have a first and a second, right? Here's my first, here's my second. The other two casted characters is the derivative of the first and the derivative of the second. Okay, so here we go. Here's our forecasted characters. I'm going to write them over here. The first function is x to the fourth. Then I'm going to find the derivative of the first function. Well, it's a power rule, right? Drop the 4 to the front and subtract 1. And you're done. You have 2 out of the 4 already. Okay, and you read it left to right. That's how you know which one's first, which one's second. Okay, the second function is x squared plus 5. And then my derivative is just 2x. The 5 goes to 0. So I have my forecasted characters. Once I get those, then it's just a matter of writing them and putting them into this setting, right? This pattern. So everything's about a pattern in math. Derivative of the first is 4x cubed times the second. The second is x squared plus 5 plus the first, which was x to the fourth, times the second, or I'm sorry, times the derivative of the second, which is 2x. Okay, so here it is again. I'm going to write it right above it. Derivative of the first times the second plus the first times the derivative of the second. Okay, now in my math lab, I haven't checked it this year, but I know last year they had it written this way. The derivative, they do that. I'm gonna have to look at it again. I think it's this one. Maybe it's x. Hang on. So the first, I'm gonna look, let me look at it before I write it down for you, because I want to make sure that it's the same as what's in my math lab. Okay, so now we just clean it up, right? We have our forecasted characters. Now I'm just going to clean it up. What does it say? It says multiply 4x cubed times x squared plus 5. So I have 4x to the 5th times 20x cubed. I'm sorry, plus, not times. So 4x cubed times x squared is 4x to the 5th. 4x cubed times 5 is 20x cubed. And then I'm going to do the same thing over here. I'm going to multiply these two. X to the 4th times 2x is 2x to the 5th. Now, do you see how I can add like terms? So I have 6x to the 5th plus 20x cubed. And that is the product rule. That's the derivative when you're multiplying two things together. Okay, so take a look at it. Any questions on where I got what? Okay, so that's with the product rule, right? So make sure you know how to use the product rule. But if I can get out of it and not have to use the product rule, I'm going to do it, because you can see it's a lot of work, right? There's a lot of moving parts. You got to make sure that you have all the right symbols and all the right signs, and make sure that you add the like terms and all of that. So there's a lot going on. But if I can look at that function and go, you know what, there's an easier way to do this. What I can do is I can distribute these through. right? So if you can distribute and multiply, do it. All right, Brian. So I'm going to rewrite this. So x to the fourth times x squared is x to the sixth. X to the fourth times 5 is 5x to the fourth. All I've done is I've just distributed. I multiplied this times this and this times this. So I made it simpler. Okay, now I can find the derivative using the power rule. So x to the 6 comes to the front, and I subtract 1. The 4 comes to the front and multiplies, and then I subtract 1. Do you see it's the exact same thing? 6x to the fifth plus 20x to the third, 6x to the fifth plus 20x to the third. So you can see, if you can see that it is simplified, and I can do that, I can multiply through and get it so that it's just a polynomial, it's much easier to find the derivative. But just know that there's gonna, and I'll show it to you, there's gonna be times where you can't get away with that. You have to do the product rule. Okay. All right, so let's try it one more time. So I'm going to jump down, because if you look at these two, if you look at number 2 and 3, number 2, I could get out of using the product rule, right? I can just distribute the 2x minus 5 through the trinomial. Number 3, I can do the same thing. I can just use FOIL and get out of it, right? So, but number 4, I can't. I cannot get out of it. There's no way for me to multiply 6x to the fourth times ln of x and make it stick. All right, I can't push the two together. So this one, I have to do the product rule. So this is my first one, and this is my second one. And there's always going to be a natural break, right? That x to the fourth doesn't belong with the with ln of x. You'll see that there's a natural break between them. All right, so first things first, I'm going to find my forecast of characters. So if you write this in your notes, make sure you know what that means, right? Make sure you know what I'm talking about when I say forecast of characters. So here we go. I'm going to do this over here. So I have my first is 6x to the fourth. The derivative of my first, 4 times 6 is 24. And then I subtract 1. And hopefully you guys are to the point now where that power rule doesn't scare you. All right, and then my second one is ln of x. And the derivative of the second, so this is one of those 4 special ones. Anyone tell me what the derivative of ln of x is?
It's just 1 over x.
Perfect. Okay. And now I have my forecasted characters. Now all I got to do is start writing them, putting them into my formula. So derivative of the first times the second plus the first times the derivative of the second. Okay, now you always want to step back and go, okay, how can I clean this up? All right, how can I clean this up? Because my math lab's going to ask you to not only clean it up, but to factor out common factors. So let's clean this up first. So there's no way I can push these two together. So I'm just going to rewrite them. But I can do something here, right? If I put this 6x to the fourth over 1 and multiply these, I get 6x to the fourth over x, which is 6x to the third. You see it? 4 minus 1, right? Using your exponent rules. Okay. Now, when I look at this, what is in common between this one and this one? What's in common? What do you
20.
see?
24x and 6x to the powers.
Okay, so what can I take out of both of those then?
A 6.
Good. And
A 3 exponent.
yeah, so x to the third. So I can factor or divide that out of both of these. So what's left when I do 24x cubed divided by 6x cubed, I have a 4 ln of x left in the first term. When I divide 6x cubed divided by 6x cubed, I have a 1. So this is my simplified derivative. And there's no way to get out of it. I had to do the product rule. Okay. All right, we got time for one more. So go ahead and try number 5. I'll give you a few minutes to get your forecast of characters, because again, there's no way I can do this without the product rule. I can't smash those together and make them all one term. So go ahead and do your forecast of characters. And I'll give you a couple minutes and then I'll write them down. Make sure you have the right ones. And then set it up and in chat, write your answer. So I'll give you a few minutes because I know they take a little time. All right, so those are your forecast of characters. So just kind of double check yours and make sure that they are the same. So with the first, I just use the power rule, and with the second, I use that specialty e to the x. So now set that into the product rule. And this is why it's a good idea to go ahead and print up that formula sheet so that you have it right there with you. So you always have it where you can use it, and you're going to get used to using it for the test. And our next test will be the Thursday before spring break. So spring break is March 11th through the 15th. So our next test will be Thursday, March 7th, and that'll cover all of chapter 10. All right, so here we go. Derivative of the first times the second plus the first. I'm running out of room. Times the derivative of the second. Okay. Now, the only thing that we can do with this one to clean it up is we have e to the x in common, right? I can't take x out because there's a 1 here and a 1 here. But if I factor e to the x out of each one, I end up with 1 minus 3x squared plus 1 plus x minus x cubed. Do you see it? So once I take this e to the x out, now I have terms that I can add together. So I have e to raise to the x power. 1 plus 1 is 2. I have, actually, let me put it in descending order. So I have negative x cubed. Don't have anything to add to that. I have a negative 3x squared. Don't have anything to add to that. I have plus x plus 2. And that is my simplified derivative. Okay, so in MyMathLab, it is going to ask you to see if you have, if there's a common factor. Okay. So any questions? Okay. All right, so I'm going to stop there because we're going to go into the quotient rule on Thursday, and then we're going to practice both mixed in with those 4 special ones. So definitely take a look at the homework for 3 or 10.2. That's just those 4 special ones. It'll go fairly fast. Use the formula sheet so that you get used to using it and reading it. And then that's it. I will see you guys on Thursday. And if you have
See you,
any
Ma.
questions,
Thank
I'll
you.
hang out. You're welcome.